Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of Mind Maps, we'll be dealing with the second chapter of the chemistry syllabus of grade 10 in CBSE. The name of this chapter is Acids, Bases, and Salts. So in this chapter, we're going to be looking at various compounds and determining whether they are acids or bases or salts. Then we're going to be looking at some reactions involving acids and bases and some salts in general. So in order to finish this chapter off easily and in order to give you a comprehensive view of everything, we've decided to use a mind map. Mind maps are excellent tools for last minute preparations, but sometimes they can get quite extensive, so therefore this video is devoted to explaining this mind map in some detail. So in this mind map, we have 5 sections. We have an overview of the entire chapter. We have the physical properties of both acids and bases. Then we look at chemical properties of acids and bases one by one. And finally, we top it all off with the types of salts and examples in common existence. So acids, bases, and salts. So the food that we eat and the chemicals that are around us can be, classified into either acids, bases, or salts. And they can be detected, that means identified, using indicators. So these indicators are substances, whether they're natural or artificial. These substances help us to determine whether a substance is an acid, a base, or a neutral substance. So when we look at indicators such as litmus, they depend on color. So in litmus acid, in the presence of acid, litmus turns red, and in base, the litmus turns blue. And in case of turmeric, which is natural, you do not get any change in acidic medium, but in basic medium, it turns red. That's why when you pass soap over a turmeric stain, it instantly becomes red. And a similar behavior is shown by phenolphthalein. Phenolphthalein is synthetic indicator, so there is no change. And in B, phenolphthalein turns pink, and we use this in later, in grade 12 and all, when we're trying to do titration. So keep track of it. Another indicator is methyl orange, and methyl orange turns red in an acidic medium and yellow in a basic medium, so therefore this shows both the presence of acid as well as base. Now, other than visual indicators, we also have olfactory indicators. So olfactory indicators include onions, vanilla, and clove oil. So in the presence of acid, they have this particular characteristic smell, while in a basic medium, they do not smell different. So therefore, these are the kinds of indicators that we commonly use in order to distinguish whether a substance is an acid, a base, or a salt. So what are we going to do in this chapter? In this chapter, we're going to be looking at physical properties of both acids and bases. Then we look at chemical properties, essentially the reactions that they undergo. And then we look at the types of salts. So basically, we're looking at some examples of salts and their functions and their uses in daily life. So now let's move on to the first topic, which is physical properties for both acids as well as bases. So an acid is a substance that is sour in taste, while bases are usually bitter in taste. Now, if you have eaten lemons or oranges, sometimes you feel them sour in taste, so that's when you know that they are acidic. So an acid is usually sour in taste, but then big warning, do not taste something that you don't know. So for example, if you were to taste sulfuric acid, you would have a burnt tongue instead of anything else. So therefore, don't try to do the taste test for every acid or base that you come across. So when we're looking at lemons, yes, it's potent enough to have a sour taste, but essentially nothing big happens. But then if you want to experience bitterness, then the best way to do that is to, taste soap. I know most of you don't do it, but then if you have accidentally tasted soap, you would know that it's bitter in taste, so therefore soap is an example of a base. Now, when you're looking at its presence with respect to an indicator, acids, they turn blue, litmus red. So we have litmus in the form of paper. So when you have litmus paper, it's usually blue or red. So an acid turns blue litmus red, and a base turns red litmus blue. So therefore, that can be counted on as a physical property. So when it is in the presence of indicators such as litmus paper, methyl orange, etc., shows characteristic properties. And the main thing about acids as well as bases that differentiates them is the fact that the ions that they release. So when it comes to acids give out H+ ions in an aqueous solution. So in an aqueous solution, acids form hydronium ions. So it's basically hydrogen plus water, so H3O+ ions are formed. And in bases, the dominant ion that is formed is OH-, so that's why they are basic. So in an acidic medium, you have an excess of H+ ions, and in basic medium, you have an excess of OH- ions. This will, feature well in our description of how we can identify whether an acid is strong or not. And another important property that is physical with respect to acids and bases is the conduction of electricity. Aqueous solutions, they conduct electricity a lot because they are passing out H+ ions, while physical properties of bases say that bases are not essentially good conductors of electricity because you have an excess of OH- ions. So these are the physical properties that are characteristic for acids as well as bases. Now remember, do not do the taste test for every kind of acid or base you see. Some of them are quite potent and they could kill you. So therefore don't do that. So, but if you're talking about lemons and soap, then there's no bodily harm in doing it other than just a distaste of something. So these are the physical properties with respect to acids and bases. Now let's jump right into chemical properties. First up, we have the acids. Now, when we're looking at chemical properties of acids, we look at certain reactions, and the first reaction is reaction with a metal. So when an acid reacts with a metal, you essentially get the salt of that acid and hydrogen. So for example, if you place in zinc, so if you put zinc granules in sulfuric acid, and then you place a candle through on top where the gas is passing through, then you can see that the gas gives the candle a pop sound when it burns, and then it gets extinguished. So this is basically the liberation of hydrogen. So according to the reaction for zinc, you would have Zn plus H2SO4 giving us ZnSO4 plus H2. So the H2 gas is liberated, and this liberated gas can be found out by placing a candle close to the airway, where you can see that the candle burns out with a pop sound. So when acids react with metals, they liberate hydrogen. And if you're looking at other compounds, say metal carbonates, so what happens is that carbon dioxide gets liberated, and if you want to find out whether carbon dioxide is getting liberated, you just pass that gas through calcium hydroxide solution, so you'll get calcium carbonate. So acid plus metal carbonate, or bicarbonate, that is hydrogen carbonate, you would get the salt of that metal plus CO2 plus water. And this is particularly visible when you use sodium carbonate, that is washing soda, or sodium bicarbonate, which is baking soda. So when you react that with HCl, which is a gas, you get a salt that is NaCl, which is also known as common salt. the salt that we usually use in kitchens. And then you have carbon dioxide, CO2, and H2O, that is water. So NaHCO3 plus HCl gives NaCl plus CO2 plus H2O. So this is the reaction that occurs here. And if you want to find out if carbon dioxide is liberated, just pass it through calcium hydroxide. CaOH twice plus CO2 gives you calcium carbonate, and the calcium carbonate precipitate gives you a lime milky appearance. So lime water turns milky because of the formation of the precipitate of CaCO3. Now, in addition to this, acids, they react with metallic oxides to form salts. Now, the reason why they react with metallic oxides is because metallic oxides are basic. So therefore, if you have metallic oxides and you react, you react them with acid, then you would get salts and also other byproducts. Now, let's jump to the chemical properties that we usually observe in bases. So again, chemical properties of bases also depend on their reaction with metals and their reaction with acidic oxides. So if you have an alkali that is reacting with an alkali that's reacting with metal, you would liberate hydrogen. Now, this is not applicable to all metals. It only occurs in some metals like zinc, which shows amphotericness. So if you have 2NaOH, that is sodium hydroxide, which is a base, plus Zn, that is zinc, then you'll get Na2ZnO2, that is the salt formed, plus H2, so that's hydrogen gas. So hydrogen does get liberated when alkali react with metals, but then this does not occur for every metal that is there. So it only reacts with some metals in order to form hydrogen. And another important property is that bases react with acidic oxides and they form salts. And the important thing to note is that bases do not react with carbonates or hydrogen carbonates because the carbonates or hydrogen carbonates are usually basic when it comes to metals, and so therefore reacting a base with that would not give any appreciable result. Now, some of these acids and bases that we've just used to react are extremely strong, while others are quite weak. So how do we determine the strength? So how to determine the strength of acids or bases? Well, the best way to determine that is by using the pH scale. So the pH scale is a scale from 0 to 14, and the neutral solutions such as water lie at 7. Anything with a pH value lower than 7 is acidic, and anything with a pH value higher than 7 is basic. And note that this condition occurs at 25 degrees Celsius. So pH is usually dependent on temperature, but then that is a study for higher classes. For now, you just know that pH is a scale that ranges from 1 to 14, and 7 is the point where neutral solutions exist. Now, the name given to pH is actually expanded as potens hydrogen. Now, the reason why it is potens hydrogen is because the pH scale measures the hydrogen potential. And the hydrogen potential is basically the negative logarithm of the concentration of H plus ions. Now, this is again higher order chemistry, so you can study that later in your higher classes. And that's why, why I just told you this is because to give you the idea that the pH scale is dependent on the hydrogen ion concentration. And if you have a higher hydrogen ion concentration, you have the place lower in the pH scale, so that means your compound has to become more acidic. If it has lesser H plus ions, then it is more basic. So that means it's ranked higher on the pH scale, which is present at 25 degrees Celsius. And this is all theoretical. Now, how do you want to determine the strength of an acid practically? Well, practically, in order to find out in which pH the acid or base is lying, you have to use a universal indicator. So a universal indicator is an indicator which shows variations in color depending on the pH, specific pH of the compound. And this universal indicator is actually prepared from a mixture of various indicators. And that's why it is known as universal, because you can find out the pH of any material from 0 to 14 using this universal indicator. Now, we move on to the final part of this episode of this mind map, and that is salts. So what exactly is a salt? A salt is basically a compound formed when acid reacts with a base to form water, and the base, it's basically a byproduct of that reaction. So acid plus base giving us water plus salt is what we call a neutralization reaction. And the reason why it is called the neutralization reaction is because water that is formed is actually neutral. The salt that forms does not always have to be neutral. It can be acidic or basic depending on the strength of the acid or base respectively. So from neutralization reactions you can form salts. Salts are also formed from other reactions as well, but then when you look at definition wise, it actually forms when acids and bases combine together and form water. So there are various types of salts. You have simple salts, double salts, and then complex compounds, etc. So in order to get into the scope of what this textbook offers, we just look at some examples of common salts. So this section that is types of salts is in a sense talking about the examples of salt that we commonly use. And the most common salt that we use is what we call common salt or table salt. It is sodium chloride, NaCl, and it is formed when NaOH, that is sodium hydroxide, reacts with hydrochloric acid, that is HCl, to form water and sodium chloride. Now, this sodium chloride is actually used as a raw material for various other chemicals such as NaOH and chlorine production industrially, and then it is used in cooking as well as flavoring. So it is pretty important in the kitchen. And also when you look at industrial catalysts, NaCl is used as a catalyst, and that's why it is being used in the kitchen. So good point to note. Now there are other important salts besides common salt that we use in our everyday lives. An important salt that we all would use in the industrial age is bleaching powder. Now, bleaching powder is represented by the formula calcium oxychloride, that is CaOCl2. So it is formed when calcium hydroxide reacts with chlorine to form water and calcium oxychloride. Now remember that the original formula for that compound is not CaOCl2. The actual composition is quite complex, but when you have to simplify it, then it comes out to be CaOCl2, calcium oxychloride. Now again, bleaching powder, as the name states, is used for bleaching various substances. It is used for bleaching textiles such as linen and cotton, and we also use it to bleach wood, which is this is usually done in the paper industry, and we're also using it to bleach used clothes in the laundry. So therefore bleaching powder is extremely important for bleaching various substances, and that's why the name. It is also, now note that bleaching powder is also used as an oxidizing agent, and so it oxidizes whatever so it easily gets reduced, and the compound reacting with it gets oxidized very quickly. And Another important use for bleaching powder is as a disinfectant. So when you have water, you can remove the germs from drinking water using bleaching powder, and that's why it is a disinfectant in water. Another important salt that we use in our everyday existence is baking soda. Baking soda is represented as NaHCO3, that is sodium bicarbonate. Now, baking soda is formed when you try to convert common salt to washing soda, and it's basically the addition of a hydrogen in the place of a sodium in washing soda. So baking soda is extensively used in fields such as cooking. So in the baking industry, baking soda is used to create baking powder that is just a mixture of sodium bicarbonate and tartaric acid, which is a slightly edible acid. And this baking powder, when you use it in doughs for various substances such as bread, pizza bases, etc., it is important in forming carbon dioxide, so that softens the bread that we find. So leavening of bread is usually done using baking soda. And another use for baking soda is as an antacid. So if you are injected by an acid, like say for example you have an ant bite, and then so if an ant bites you, then an ant injects acid into you. So therefore, if you rub baking soda over that, then the swelling will subside, because that is a neutralization reaction taking place. Now, washing soda is another important compound. This is basically Na2CO3.10H2O, and it is formed when sodium carbonate reacts with, sodium carbonate get mixed with 10 molecules of water. So basically, washing soda is hydrated sodium carbonate, and it is a very important compound. Now, when it comes to water, washing soda is used to remove permanent hardness of water. It is also used as a cleansing agent, and hence the name washing soda. Then we can also use it to make compounds make substances such as glass, soap, paper, borax, etc. So washing soda is pretty important. And the final salt that we'll be discussing in this chapter is plaster of Paris. Now, this is usually discussed in the section, are all salts hydrated or not? So all of the salt, so most of the salts, like for example, sodium carbonate, are not just the chemical compound that is sodium carbonate. So washing soda is basically sodium carbonate, which is hydrated with 10 molecules of water. So in various salts, various degrees of hydration can also form different salts and different compounds. And a unique example of this is plaster of Paris. Plaster of Paris is plaster of Paris is calcium sulfate hemihydrate. So it's basically CaSO4 times half H2O. Now you might wonder how it can be half H2O. That is because 2 CaSO4 is binding to 1 H2O molecule. So calcium sulfate hemihydrate, that is plaster of Paris, is basically calcium sulfate which does not have adequate amount of water. Now if you put in water, that means if you add water to plaster of Paris, it after some time it hardens into a solid mass which is quite strong, and that solid mass is called gypsum, which is CaSO4 times 2H2O. So therefore, plaster of Paris is immensely useful in sculpting and building, etc. And it was found it had origins in Paris, and that's why the name plaster of Paris. So that concludes this mind map. We looked at acids, bases, and salts, physical properties of both acids and bases, chemical properties, indicators, as well as types of salts. Now, it's not just mind maps that we have to deal with. we can also use flowcharts in order to deal with exams. They are also effective at last minute preparation. So this is a flowchart for the chapter acids, bases, and salts. So we have a lot of organic acids. So these are acids which are found in nature. So for example, vinegar that we use in kitchens is actually acetic acid. The guavas that we eat contain oxalic acid. Lemons contain citric acid. That's why they're called citrus fruits. And tamarind contains acids such as tartaric acid. Curd is usually made using lactic acid. Ants, when they sting us, they have a concoction of formic acid, and oranges and gooseberries, etc. The fruits that have an excess of vitamin C, they have ascorbic acid. Ascorbic acid is the chemical name for vitamin C. Now, when you look at acids and bases, you have physical properties and chemical properties. These are the properties that we've discussed. Sour, blue litmus red, forms compounds, and H plus ions, and aqueous solution conducts electricity. And bases are bitter, red litmus turns blue, OH minus ions are formed. Then we have chemical properties, that is reaction with metals, as well as reaction with acidic oxides and reaction with metal carbonates in the case of bases and acids respectively. And then finally we have the types of salts. Common salt, again discussed. Bleaching powder discussed. Baking soda was discussed in the mind map. Washing soda and plaster of Paris. So here you have another reaction for plaster of Paris. So this is basically the dehydration of gypsum in order to form calcium sulfate hemihydrate. So that concludes this episode of Mind Maps. If you want to access more of our useful and interesting content, then don't forget to subscribe to our channel, which is Brain Blitz Audios. You can also hit the notifications button in the space below the video so that you can get latest notifications regarding our content. If you want to rewatch some of the mind maps for grade 10, you can hit the link for the playlist in the description box down below. So until the next webisode, take care, stay safe, bye-bye for now.